Alright guys, welcome back, and today we are going to be getting into 7.2, which is verifying trig identities. And we're essentially going to be using the trig identities that we learned before, and we are going to show that they equal, or we're going to show that one side of an equation equals another side of an equation using those identities. So for the think/rump, I have how would you verify that x plus y all in parentheses squared equals x squared plus 2xy plus y squared? Well, I think what you would do is you would take this left side, x plus y, and you would say, hey, x plus y squared is x plus y times x plus y. And then you would multiply this out, right? You'd say x squared, or x times x is x squared, x times y is xy, then you're going to get another xy, and then you're going to get y squared. And then when you combine like terms, you have two xy's plus y squared, and hey, that ends up equaling what we had on the right side. So we just showed that they are equal. And now we're just going to do stuff like this, but with trig identities. So verifying trig identities involves manipulating one side of an equation into the same form of the other side of the equation. This often involves using trig identities and basic properties of algebra. Now, one important thing to note here is you can't perform operations on each side of an unverified identity as you usually do with equations, because an unverified identity might not be an equation, right? Like one side of something might not actually equal the other side, so the properties of equality might not apply. So essentially, you can only algebraically manipulate a single side. And here's just a few tips for verifying trig identities. And again, this isn't going to be 100% of the time for one of these, or necessarily like an order to do things, but just some tips. Usually you want to work with a more complicated side of an equation. It's easier to simplify a more complicated side than it is to take a more simplified side and complicate it. Substitute trig identities. Again, we're dealing with trig functions. We're probably going to have to use the trig identities we learned. Factor or multiply to simplify expressions, and express trig functions in terms of sine and cosine. So like tangent is sine over cosine, secant, cosecant, stuff like that. Put those in terms of sine and cosine can help. And the disclaimer here is there is no cookie cutter way. Like, you can write down these tips, but just following these every single time isn't always going to get you there. But it's more of just about like working with these, and the more you work and practice on your own, you'll kind of gain a little bit of foresight and become more proficient at these. So I think maybe one of the best ways to start these is just to go through an example. So verify that secant squared x minus tangent x times cotangent x equals tangent squared x is an identity. So what we're really doing is we're asking, is this actually equal to tangent squared x? Well, like I said, I'm usually going to want to, tangent squared seems pretty simplified, right? So I'm going to deal with the more complicated side, which seems to be this one. So we have secant squared x minus tangent x times cotangent of x. Now I'm just looking at this and I'm just thinking, hey, what can I do to this thing? Well, we know that I see tangent and cotangent, but I know that cotangent is 1 over tangent. So really, and again, our equal sign kind of has a question mark here. So really, we get secant squared x minus 1. Tangent divided by tangent is just 1. Something divided by itself is 1. And then here, we're kind of done, right? But just for the sake of continuing, we know, maybe I'll write in a different color off to the right, we know that secant squared of x, we know that secant squared of x is tangent x, or tangent square root of x plus 1. That's one of our Pythagorean identities. So if we substitute that in for secant squared x, tangent square root of x plus 1 minus 1 equals tangent squared x. And again, we're asking, is that equal? Well, and then plus 1 and minus 1 cancel out, and we have tangent squared of x equals tangent squared of x. So we have just verified that identity because it turned out to be true. While working on a mathematics assignment, a group of students derived an expression for the length of a ladder that, when held horizontally, would turn from a 5-foot wide corridor into a 7-foot wide corridor. They determined that the maximum length L of a ladder that would fit was given by this equation here, where theta is the angle that the ladder makes with the outer wall of the 5-foot wide corridor. When their teacher worked the problem, she concluded that the length here turned into this equation are the two expressions equivalent. And so for this one, it's put into a word problem, but what we're really asking is 7 sine theta plus 5 cosine of theta all over sine theta cosine theta, does that equal 7 secant theta plus 5 cosecant theta? And again, I just kind of start out by looking at these, and again, this is a question, are these equal? We have to show that it is or is not. And I'm just saying, what can I do with this stuff, right? I can't cancel these sines and cosines because of this plus here. So this side's kind of weird, but let me just work with this right side for a second. Secant, we know, is 1 over cosine, and we know cosecant is 1 over sine, so we could really just throw cosine and then sine in the bottom. And now we're looking really close to almost what's over here, right? I don't really want to rewrite all this, so let's move this, just pretend we move all that down. But we have cosine and we have sine on the bottom, and here we have sine times cosine. Well, maybe my brain is saying, hey, let's get common denominators here. So to get common denominators, multiply this one by cosine over cosine, and multiply this one by sine over sine. And we can do that. We're not changing anything because cosine over cosine is going to be something divided by itself is 1. Multiplying something by 1 doesn't change it. Same thing here. So what we really get is 7 sine of theta all over sine theta cosine theta plus 5 cosine theta all over, and again, this was a question this whole time, this equals all over sine theta cosine theta. And then in the end, we see, now that we have common denominators, we can just add across the top 7 sine of theta plus 5 cosine of theta all over sine of theta cosine of theta, right? And now here's, if we brought this, all the way down to here, these two things are equal. We just verified them, right? All we did was move things around over here, a little bit of algebraic manipulation, and we showed that these two things are equal. So we have verified it. Verify that this equation is an identity. So for this one, again, if I see cosecant and secant, I kind of just right away want to turn that to sine and cosine. So I know cosecant is really sine on the top, so I have sine of A times the sine of A, and then I know that secant is really cosine on the top, so I have cosine of A times the cosine of A, and I'm just going to leave this stuff alone for now. Well, now sine squared of a plus cosine squared of a well, this is something we know, right? This is 1, right? And then cosecant squared minus cotangent squared, well, that's also 1, right? If we look at our identities, we had that 1 plus cotangent squared equals cosecant squared. So if we had 1 plus cotangent squared equals cosecant squared, then if we subtracted that cotangent over, we'd get 1 equals cosecant theta minus cotangent squared theta, which is exactly what we have here, right? So we have 1 equals 1, which is true. And again, if I see some squareds like this, I'm kind of saving them because I have a feeling that, like, once I see those squareds, that one of our Pythagorean identities are going to come through, right? Which it did. And for example 4, I have find a numerical value of 1 trig function of x if cotangent of x over cosine of x equals 2. And this one is worded a little weird, but it's essentially just asking simplify this down to 1 trig expression, right? Because 1 trig function. And numerical value is just like 2, right? 2, 3, 4, a number. Right, so it really wants us to put this down to a single trig function. And we know that cotangent of x is cosine of x all over sine of x. And then we have that all over cosine of x equals 2. Well, we also know that this means cosine of x all over sine of x times cosine of x. That's the same thing. And then the cosines can cancel. And then we're left with 1 over sine of x equals 2. And we know that that can be simplified to cosecant of x equals 2. And that's exactly what it wanted, right? 1 trig function, a numerical value of 1 trig function. Here's 1 trig function, and here's its numerical value. So that is going to wrap up 7.2. I know the homework might be a little tough when we first try it, but we will spend a lot more time on this stuff.